And but I'm the application specialist or engineer, whichever way you look at it. And I will do everything from, set up a simple 3D printer to an advanced CNC system and train the teachers. And we'll do everything from just the basics to get into project-based workflow and talking shop about lab setup. Pretty much you name it. If it falls under the umbrella of tech education, AET Labs has their hand in it in some respect or another, from the grant funding side all the way to the end use. And I love talking about the nerdy stuff. So that's what we're going to get into today, a little bit. So Paul and Dave, I want you to by all means jump in if you have any questions. Usually when we do our demo and discuss, it exactly is that. It's a demonstration of the technology or some topic of the technology, and then a discussion where we just kind of freely talk, answer questions, learn a little bit about what you're doing, and so on. And we try to do these demo and discuss sessions monthly throughout the school year. Okay, so our topic today, give me 1 second here. Just gonna go ahead and share my screen. And Kristen, we're recording, right?
Yeah. Mm-hmm.
So I'm just popping over to the website where you guys registered. So the topic is a review of 3D printing and mechanical tolerance. And mechanical tolerance is a very deep subject when it comes to machining, additive or subtractive manufacturing. So we're just going to touch on a little bit here today, like what is mechanical tolerance, and down here, as we can see, how does it factor into 3D printing parts that are meant to work together. The other question, which is good for users of Fusion 360 and probably some other software too. Dave, you might be able to speak to this, maybe in SolidWorks, but you can import McMaster-Carr parts or hardware directly into projects. And when we say McMaster-Carr, we're talking about this touchstone for ordering hardware of all types. McMaster-Carr is a very well-known hardware supplier, and this is their website here. Okay, so mechanical tolerance. I think the first thing I'm just going to do is jump right over to my CAD software. And, Dave, you mentioned Onshape, and I have not spent much time in Onshape, but the other day I met with a teacher who he had some questions about the laser cutter workflow and like making 3D designs to bring to a laser cutter. And I met with him and I said, okay, I'm not entirely sure about Onshape, but let's just jump in and give it a try. And within 5 minutes, I was able to navigate Onshape and figure out how to work through that process. So I think that a lot of this transmits very easily between software like Fusion 360, which is what we're looking at now, SolidWorks, Onshape, Inventor. So I'm not sure if Onshape has the ability to import McMaster-Carr parts, but it's something it's worth checking into. Right now, we're just looking at a very tiny sample part that I designed. It's a very simple gear assembly. I think I have a section analysis here. Yep. So if we take a look at our analysis, we can see our gears are very close together. We'll take a closer look of the actual part here. Just give you an idea. Let's see if I can do a quick inspection here. So we're looking at it's really probably about 0.2, but in this case, face to face, or closest point here is 0.221 millimeters apart. And when we talk about mechanical tolerance, the other term that comes into play, and I'm just going to kind of bring this up so we can have it on the screen here. I don't have like a formal slide, but is dimensional accuracy. And and dimensional accuracy is really the foundational factor before you even get into mechanical tolerance. So if we look at our model here that was designed with a distance between where our gears are going to touch of roughly 0.2 millimeters, and then we take this design over to a 3D printer, we have to have some fundamental understanding of the dimensional accuracy of the printer. Now, some printers, if we like pop over to, let's see, where's my MakerBot? If we pop over to MakerBot method specifications, I just had this open. Sorry, give me 1 second here, guys. There we go. We actually get a dimensional accuracy value here of plus or minus 0.2 millimeters. It's actually very rare that you would see this on many 3D printers. Like if we pop over to Form Labs and we look at the Form 3, and we scroll down and look at some of the information that they have here, technical specifications, they'll give your layer resolution, your XY resolution. But first of all, the technology is different. Resin-based printing like Form Labs, or in this case, projection-based photopolymer 3D printing is based on pixels as opposed to the method, which is a typical additive manufacturing where a extruder follows a tool path. So the dimensional accuracy is going to be different with respect to that.
Yeah, Adam, if I could just
talk
a little bit. So, so that's about, plus the 0.2. I just did a little thing on the conversion. So that's like plus or minus, 0.008 accuracy. And, I've used quite a few different 3D printers, except for the Form Labs. I just printed out something last week at QCC. And I think students in general are very misinformed, Adam, about, a lot of students think that if I create a model, say in Onshape or SolidWorks or Inventor, and I print it out on a 3D printer, I'm going to get exactly what I actually designed the part to. And I find that a lot of 3D printers have a real issue with holding tolerance. It's a problem with parts fitting together correctly. It's not as good as subtractive. And I think a lot of students get misinformed about, they think it's that easy to go from, part model to 3D printing.
Sure. Yep. And I think you're right with some respects, especially with FDM or fused deposition modeling, where it's melting plastic, right?
Right.
Melting filament. I will say the reason that I kind of bring up this, the method spec here, is that this 0.2 is pretty broad. I mean, 0.2 is for mechanical parts working together is it seems like a small amount, but it's actually, it feels a lot bigger when you're doing
exactly. Yeah, because
right.
Most of the drawings I'm doing when I'm teaching mechanical design, we're doing the standard, plus or minus 5 thousandths on a 3-place tolerance. And I find that a lot of the 3D printers, like you said, this is holding 0.008. I find that is not that great. It's not that great.
Yeah. So, before I kind of move forward, just because, Paul, you're bringing this up, what I think I'm going to do is just share this slide over here, because I think this will be a great place to move forward to. So let's just talk quickly about variables of dimensional accuracy right out the gate. All right. So the first thing to talk to your students about and to kind of educate yourself about is that there are many factors. And the first one being hardware. The printer itself, right? The motors, the staging, and by staging I mean the gantry, the bed. Maybe the bed moves up and down. Maybe there's a motor, there's going to be motors doing that, or driving the gantry left and right, XYZ, up and down. The actual extruders, what the extruders are made out of. I mean, there are 3D printers out there, like Lulzbot is an example, where they have parts that are 3D printed. Like it feels like maybe 25% of the printer is actually 3D printed. On the other hand, we work with like Stratasys 3D printers, which are higher end 3D printers, and they have the hardware is a lot more consistent and solid. So just the printer itself is plays a huge role. If you set up like 3 different 3D printers and you printed with the exact same filament, I'm talking about the same manufacturer, same filament, you're going to have a different dimensional accuracy in the 3 machines just based on their hardware. How well were they built and designed? And let's go on to other factors that still play a role no matter the printer quality. So material. And this goes into the world of chemistry, which is one thing I love talking about with people, because material physics is a very real thing. Thermodynamics, chemistry in general. This is a huge, huge thing here. You're melting, in the case of FDM, you're melting a solid, right? And you're letting it cool and solidify again. And that will play a huge role depending on the different types of material you're using. If you're using something that is designed to be a very tough, rigid material like ABS, for example, you'll probably get a higher dimensional accuracy than PLA, which has a lower, I should say, temperature resistance, right? So, if it's in a warmer environment, that PLA is going to start to melt before something like ABS would. And then of course resin-based printers, same thing. Resins are, in this case, photopolymers, so they're using a UV light to change it from a viscous sort of slimy resin into a hard material, right? But still different mechanical properties on all of these materials. They all plays a huge role. Part geometry is another one, right? So if you have a student like designing a pyramid, let's just say like a very basic sort of pyramid shape, and they measure the base and they measure the middle of the pyramid and they measure the top, and then they go and they find that the accuracy is A, B, and C, and then they move over and they make a cylinder or a cube and they find it to be different. That's going to have a bearing. You know, if you have like an area with complex geometry, and let's take, for example, the picture that we're looking at right now, just this little, this screw and, you know, bolt seating for the screw. If you're measuring the accuracy of, let's say, a simpler piece of geometry, like the cylinder head of the screw versus the actual threads, you're probably going to get a different dimensional accuracy by some degree, somewhere in between, maybe 0.1 or 0.2 in this case, because this was actually printed on the MakerBot Sketch, which is really their entry-level printer. So part geometry has a bearing, and then this one, you know, I'm not sure how much you folks are spending on this side here, but I wanted to bring it up because MakerBot particularly is very open-ended with playing around with the settings with respect to this part. So software in the final program or code, which dictates things like build speed, extrusion temperature, these also can play a role, right?
Yeah, definitely. Yeah.
Yeah. So
Yeah.
so yeah.
Yeah.
So Paul, you have messed around with
Yeah, I mean,
MakerBot specifically?
no, I actually have a cheating machine,
Mhm.
and I use Cura. They have that type of software. I have it actually at home. I have a cheaty, and like I find that on that same subject, there's a lot of different modifications I have to make, especially in speed, you know, feed speed rate, especially with a carbon fiber. I have to slow it down about 20, 25 milliseconds. And then the other thing is one other question I had while on the subject of dimensional accuracy. One thing I'm noticing, Adam, on FDM printers, and I wanted to get your response on this, your idea on this, is that on hole tolerances, through hole tolerances, I think what's happening is on FDM, is it true that the kerf, the nozzle kerf, like I use like a 0.4 millimeter nozzle, is the kerf on the center of the geometry? Because I noticed that on machines that I've been using with FDM, everything generally comes undersized about 10 to 15 thousandths, which would
Okay.
be about the 0.4 millimeter kerf if it
Yeah.
was right on the actual line of the circle. Is that
So
what happens, or is the compensation to the outside on a circle?
okay. So this is a great question, and I'm gonna pull out the big guns for this. I'm gonna open up GrabCAD Print, so we can actually see a toolpath and a better simulation. So in what I have open in the background is MakerBot Cloud Print.
Mm-hmm.
And Cloud Print is, you know, it's actually very versatile for changing settings, but as far as the simulation and understanding what's going on with the toolpaths, it's not as clear as Cloud Print. So give me 1 second here. Let's go into bring open a model here. So GrabCAD Print, if you're, you know, Dave, for you, which I don't think you guys don't have a Stratasys machine, is that correct?
Correct.
Yeah. And for anybody watching the video after the fact, GrabCAD Print is the proprietary software, like slicing software that you would use to prepare models. And what I'm going to do here is just pick up a template for something FDM. Let's see here. We will do an F170, which is now their kind of entry. And when I say entry level, I mean their least expensive printer, but it's still a very, very high quality printer. Right. And let's go into our slice preview. Okay. Okay, so Paul, correct me if I'm wrong, but your question is whether or not when the extrusion is happening, if the tool path, because right here we're seeing a very good kind of rendering, like a nice high quality rendering of the bead of plastic that's being extruded, right? Your question is, should we be expecting that that tool path is right in the middle of this bead, or the bead is accurately being laid down, right?
Yeah.
And my answer is, well, for a Stratasys system, surely, but my answer would be yes, that it would not be offset. It is not uncommon, or I would say it's not common for a 3D printer to be laying down for its tool path to be on the outside or the inside of the width of this bead.
Right.
All right. Now, depending on the system that you're working with, it's just, you're going to, again, you're going to be working with those variables that I was talking about earlier.
So Adam, so that being said, right, when you have a 0.4 millimeter nozzle, which I guess is that like a standard size, generally 0.4 millimeters, right?
I think it depends on the system, but
yeah,
I've seen 0.4 be very common. Yep.
So with 3D printing, and again, I'm kind of new to a lot of this too. With 3D printing, we're gonna have an issue with tolerancing. If it's laying the path down on the center of the geometry, both on the through holes and on the other dimensional accuracy of the part, it's not gonna come out 1-to-1. It's just not gonna happen.
Let's
right?
talk about what might be happening in the back end, though, right? So the people that are engineering these this software, for example, they're not just like saying like, okay, well, this is the tool path and that's the end of it. They are absolutely accounting for the fact that there's a width right here. Right. That this line here has a width. So let's say the width of this line itself is somewhere around 0.3 or 0.2. It might be more closer to like 0.3 or 4 millimeters. That their code is automatically going to offset the tool path based on the final geometry of the part. Okay. So, and again, this depends a lot on the software, right? The software engineers, the manufacturer, the company. Like there are so many variables. But let's demystify this. What's the solution here?
Yeah, that's the ultimate question, right? What do we? Because then we start fudging the part and everything, and so on and so forth.
Right. So my solution is to start with a design, like kind of a control point of something like this. This is something that's nothing fancy at all. And the whole point of this is to make a part that tests both X, Y, and Z mechanical tolerance. And like, what is the tolerance and like kind of that dimensional accuracy gap that we have when we're 3D printing on a specific printer with a specific material. And once you figure that out, and you could run like 5 tests if you want, and kind of, find the average between them, especially if you're working with like a MakerBot replicator, which is like at this point kind of an outdated printer, but still it's still a workhorse, You find that sweet spot and then you document that. Okay, you're printing with PLA and you learned that your leeway is on that MakerBot replicator is between 0.1 and 0.25 or something like that, right? All right, so the first thing you're doing is you are making a tolerance test. You're making some test parts that you're going to measure. And you don't even really have to do like what I do this here just because I like to have the like parts that are going to interface together, but you could simply do a series of shapes, right? You could do cylinders, pyramids, cubes or rectangular prisms, and get your calipers out and just take measurements and document those measurements. So that's the first thing you're going to do is make those test parts before you move forward.
Can I ask a question?
Yeah, please.
All right. We've been with my students, we've been mostly doing the guess and check approach. And I love the idea here of actually being very systematic about it. And that's like, yeah, actually using forethought. Is if you're saying you have a tolerance of, 0.2, 0.1, is that on the diameter, or is that where is that measurement begin and end?
Sure. All right, let's take a look at this model here.
You're speaking to a person that was an engineer for most of college, but then ended up with a psych degree and is now only teaching mostly engineering and physics.
You're making it sound like I have to give a really, really intelligent answer. Okay. Okay, I just designed this today. It's a chain link, specifically for the MakerBot method. So I designed it to be printed, so it doesn't get it's already assembled. It's printed in one go. I'll actually show you the physical model in a few minutes. And let's take a look at our sketches here. So the main thing that matters in this case is the first sketch here. So here's my sketch of the top view, and I have a couple of things here that we want to look at. We have the dimension, because this fork, the top fork here, is going to be fitting into the bottom here. And our dimension there is 1 millimeter. I went really loose there just because I wanted some play. Now I know with 1 full millimeter, I'm not going to have any issue at all. All right. So moving on from there, and I have about the same distance here as well. Moving on from there, one probably more important one are the cylinders and kind of our bearing opening here.
Yeah, your clearance hole, yeah.
So let's take a look at our first cylinder. Is a 5 millimeter diameter, and of course, my goal here is to just make that this can be whatever. I just want it to be substantial, and I want it to be a solid anchor point. So that's going to sit at 5. And then we have our hole in the back here, which I've done to 6, right? So what we're looking at here just going to draw this out right here.
So you get a 20 thousandths radius clearance.
Whoops. Just happened there. I think I just did my measurement wrong. Okay. Yeah, and I don't think I can actually give a radius measurement here. I think I'm sorry, a circumference measurement, but we know that it's going to be 2.5 and 3, right? So we want, that's an important value, is the circumference as opposed to the not circumference, I'm sorry, not the diameter. This is the diameter. The radius is the important value, right? So we have 2.5 here and 3 here. And the difference is going to be that distance from here to here, right? So that's our 0.5. And that is, Dave, what we're working with here, is we want the distance between here and here. Now, obviously for circles, it's going to be universal all around, right? But with a cylinder, with like a dowel passing through like a cylinder, the whole entire distance, or I should say the total distance, is going to be important, because this thing can move around, right? It will be able to kind of like bounce. This edge will meet here and be able to flex between here and the other side. So really, we would be looking at a total of 1 full millimeter tolerance.
That, Adam, that's really the challenge I'm finding. That's the challenge with 3D printing, is knowing how tight or how loose can I be on the printer. Right. And also, like you were pointing out earlier, the chemistry of the different materials, PLA, ABS, carbon fiber. That's really the challenge, is, sure, designing your part to give you exactly what you're trying to achieve, with right, what type of tolerance. That's the challenge.
Guys, we're kind of cruising forward here. I want to just show you one quick thing before I talk about a couple of other things, because we do wrap up around 3:30. So one of the things I wanted to cover was bringing in McMaster-Carr components so you can experiment with the students. So right now, this is a really great example. And Dave, if you can't directly import to Onshape, you can always go straight to McMaster-Carr's website and find some hardware. And look at this, CAD. Right away, like a few clicks, you get to an item in McMaster-Carr. You can go into product detail. You can get some specific information, but look at this. You can go right into this CAD dropdown, and you can select any of these and export the actual CAD model of this hardware. Now, and Paul, I think you'll like this too, because how are all of these components made, right? They're either made by molds, metal molds, or they're made by subtractive manufacturing, which is going to give a very, very, very tight
definitely
tolerance, right?
I've used McMaster-Carr in my whole career, Adam. It's great. All my fasteners and brackets and all that stuff I download, like step files. I just file. Yeah, Dave, you can just, if you want to probably bring it into Onshape, you could just download like a STP file, and I just file, and then convert it over. Yeah, it's so really it's really great to have that website.
Same process here, except Fusion just gives you an insert McMaster-Carr component drop down from the insert menu, and it gives you a little like a small pop-up window. And then I can go in and find the specific screw that I want.
Saves a lot of time.
Yeah, it's nice. Yep.
Can I ask a question? Just a little tangent. How are you familiar with the Fusion 360 Chromebook experience? Is that improved?
I don't know. I've worked with some teachers who are using it, but I have not used it myself.
I played around with it. It was so laggy. I just stepped away and was like, no, not going to happen.
It's very new. Yeah, it's very, very new. Yeah. Okay, so going into step and download. And just like that, we have our part. Now, the reason that I like this as a application in the classroom is if I go and find the nut counterpart for this and 3D print them as they are, you should have your students do it. Have them import, a screw and a nut, or any parts that are meant to fit together with this, but definitely screws and nuts, and have them 3D print it, and it's not going to work. Yeah.
Adam, you're the only one that's ever said that. Seriously.
I am?
Yeah, because a lot of teachers believe that it's just like I was saying earlier, that you can create a model and, print it out in 3D and it's going to work. It's a little bit more involved than that.
They don't print very much.
Yeah,
well, first of all,
Reds don't print very well usually. Yeah.
Let's take a look here. I have to bring this over, I think. Yeah, here we go. So these are the components. These are two counter. These are meant to fit together. If I ordered them from McMaster-Carr, they would, right? They're machined metal, steel in this case. And let's just take a look at a section view here. And move this screw. So this is a section view that's directly in the middle.
Mm-hmm.
Oh, you know what? Maybe this one has this one. This one may have been affected. Hold on. Oh yeah, yeah. So that one, I'm sorry, that one was definitely that one I had already changed. I don't know why it's not allowing me to go back. Base feature. Let's try this. Oh, you know what? I think it's not. I think I have this, so it's not actually capturing the changes that I make. So let's do this. Let's just go and do one offsets. Yeah, I think it's going to take too much time to do this, but what I was hoping to show you is that if we had these in their original imports, oh, this one, no, this might be it. Hold on.
There you go. There it is.
Yeah. So this right here, this would be flush, right? So this gap right here, they would be touching each other. Like there would essentially be no gap there because the tolerance on the tools that McMaster-Carr is using or whatever company they contract with is so good that there's barely any tolerance gap. So in bringing this into my CAD software, I can go in Fusion. This is pretty easy, but I can actually go in and select faces and do a very simple press pull. I think I might want to do it to everything. And right now it's actually giving me a value. Oh no, there we go. Okay. And I can say negative 0.1. All right. And see, it just bumped out there.
Mm-hmm.
And if I go in the other direction, 0.2. Oh, maybe one. There, is it doing 0.2?
Mm-hmm.
Yeah, a little laggy here. I have a bunch of things open, but you guys get the gist of it. So we're changing the geometry with a pretty simple process of press pull by either adding or doing a negative or positive value. In this case, it would be positive because it's pressing inward, and it's simply just scaling it down uniformly. So the tolerance, so we have a little bit of a gap here. And there's a little bit of a tolerance that allows us to 3D print with something that's going to give us a final object that's like negative or positive 0.2 millimeters off. And on that note, let's go over to my workbench. All right, can you guys see this okay?
Yes.
Let's see here. And here is the result of that. And that was probably I think that was, I did a 0.1 and 0.2,
Yes.
right?
Yes.
And this
it threads
I mean,
okay.
it's smooth. It's very smooth. Yeah.
Is it? Okay.
Yeah, it's
Okay.
huge, right? So that, you know, that's one drawback, right? If you tried to do something like this, you know, that was like a very much smaller, something like this, for example, you would be hard pressed on a FDM 3D printer.
Mm.
The other thing I want to point out is this was done on the method. Now, this here was done on the sketch. And if I hold this close, you can see that I don't think I changed the end of the threads. You can see they're pretty sharp.
Mm-hmm.
And it came out pretty good. But some
Mm-hmm.
printers may not yield that good of a result.
Mm-hmm.
So you might have to soften these the actual edges of the thread.
Mm-hmm.
But on this, this was printed with a soluble support. So I could really kind of get away with some weird geometry. One interesting thing I did want to point out with respect to soluble supports, and I'll see if you can see this here. Can you see this ridge right here where it looks like it's elevated?
Mm.
I was
Yeah.
admiring.
Yeah.
Yeah, so this was printed in this orientation, and there was soluble support right down here.
Mm-hmm.
So this is a factor that comes into play when it comes to soluble supports. And you can go into, like in MakerBot, you can go in and say, I actually want to experiment with having this be further or closer to the model. But it didn't, in this case, it really didn't matter. It still produced a really good fit. All right. So this is really good. The tolerance on this is tight, and it's a really good fit. And why couldn't you use this in like a prototype robotics project or some sort of electronics housing, right? I mean, it's a pretty strong piece of hardware, and it's not even fully like printed 100% fill. It's hollow inside to some respects. So let's see what else I have here that I can show you guys. This is probably one of the least practical ways to use 3D printing for mechanical parts, is like a bearing, because it's just kind of plastic on plastic, and it leaves it very rough. But it's still, I mean, it still will spin, and it is still you know, an interesting kind of project to experiment with for tolerance. Another one, this is a very simple application here. So I was telling Kristen about this when we were getting started. In our like washing machine closet, we have, I just put a screw in the wall to hold a broom, you know, just because I didn't want to take the time to do anything else. And eventually I just designed this little broom hook. But this is great, because now we're designing for interface with a subtractive manufacturing part, and to interface with a 3D printed part. And this here, you can actually see there's quite a lot of wiggle room. I'd need to go back to the design to see what I did here, but you can see that there's a bit of movement here. This wasn't a huge, right? This is all the pressure is this direction. So I wasn't too concerned about that. But that's another thing to talk about the students with, right? Like, where is the load? Where is the pressure being applied? Where are the parts actually touching? Right. So this was a cool little, you know, just simple project. Down the line, you have, or up the line, I should say, this is, you can actually see the ridges in this, but this was printed on a Stratasys Origin machine, which is a very high-end resin printer. But this is cool. This is something you can absolutely design for FDM. And this has a little ball and socket joint. You can totally make a ball and socket joint with FDM. And probably at this size, maybe this is kind of pushing it here. This is a little maybe too small for FDM, but yeah, this is great. And yeah, and what I love about stuff like this is, you know, you're having your student design for an anatomical model that could then be passed along to another department of the school or another class in the school, a biology class. And then I think finally here, I just have this guy, which is in the water bath. But here's the
Oh, there's your link. Yeah.
here's the link. Yeah, and it works. It works great, except I failed at one part of the design, and that was the range of motion. So I was very I didn't fill it these corners enough, so you can see that it actually it'll hit the corner. If I filleted them more, I would have a broader range of motion. But then again, for something like this, you need it, right? You know, depending on how much do you need it, because look at it. I mean, it almost curves like 180. But this is a totally, like, mechanically, this is certainly a viable option for a design if you're prototyping something and you want to like 3D print some gears. If you remember when we looked at this design, the gap here was 1 millimeter, and it's huge. It's huge, right? So the method's precision is pretty good. And what did I say it was? 1 full millimeter inside as well, I think.
Yeah, 40 thousandths. Yeah.
Yeah. So it's pretty loose, but it also, right, when you're doing something like this, you might want it.
Good prototype. Good one.
Yeah. So yeah, but this is cool because this is usable, right? I mean,
And that was printed on FDM. That was FDM.
This is the MakerBot method.
The MakerBot. Yeah. Oh, good.
And I think we'll show you guys. Yeah. So this is the method and the sketch next to each other. Yeah, the method's pretty neat. It has, I mean, it's, you know, it's MakerBot's top end printer in this case. It's pretty nice setup. But, you know, as far as like when you want to stop designing for this type of printer, right, where you have to clip off the supports and have a little bit more versatility with your geometry like this, right? So you don't have to assemble. It's already assembled. The method's a pretty cool option. And then, of course, the next step up would be Stratasys. Cool. All right. Well, that brought us pretty far. You guys, let me give you a few minutes here. Do you want to comment on anything and touch base on something I covered, or?
I'm relieved to hear other people are doing the same stuff. And I like hearing different ways to just tie the teaching of this into projects. So that's something I'm sitting here taking some notes. I'm definitely going to tackle a couple of these as like little projects for kids to do, and then, okay, go run it and let's see what that looks like.
Yeah. Anything, Dave, anything popping into your head now that you're kind of like in the space?
Well, here, I'll show you. You asked me to show some stuff that we've done, right?
Yeah, sure.
Can I show you my screen, and I'll show you, like, yeah. Hopefully this assembly goes. I have not. Yeah, there you go. How do I share my screen?
So you should have a share icon if you're in the Teams app. There should be like on the bottom, maybe.
Are you able to share?
I'm not an organizer or presenter.
Okay, I could switch you to presenter and then you'll be able to share.
I still have my training wheels on.
Oh no, it's not you. I just have to make you a presenter. Okay, so I just made you the presenter.
There we go. Window. So we do. Oh, it says, oh, I need to give permission. Privacy. Where's that?
That sounds like something on your side.
Oh, darn. Ready? We'll go.
Yeah, let's just do it. Yeah, by all means, just go ahead. Yeah.
There.
Oh, nice. Okay. Yeah.
let me see if I can make this work. So we do a project where the art students design projects, and then come up with ideas for like household items, then my students make them. So this is one of the more high-end projects from last year. It's a frog themed cell phone stand.
Can you turn your oh, actually, I don't know, Kristen, are you, if you pin him, will the recording will the recording see it like that?
It's just saying pin for me. Oh, spotlight for everyone.
Yeah, there we go.
Yeah.
Okay. So this has got slider joints, right? So the assembly, I don't want to mess up their project. So this will slide forward and back. I'm afraid I'm going to blow up their project. Then you also have a whole bunch. You've got also a slider in the legs, so it can, go up and down to account for the different leg positions. And you got a whole bunch of ball and socket joints, including the back here. We ran this on a method. It took a good amount of running, but we really needed that support material to get this to come together because there's so many overhangs in it. So that's a really high-end project we've had students do. The classic one is just Estes rockets. And there it's all about, okay, how big do you have to make? What I do is I have a student design sort of alternating parts. So one student does the fins, the next person does the lower body tube, the next one does the upper body tube, and then back to doing the top fin. So you have to work, you need to collaborate with somebody else to make your designs mash up. And it's about communication, sharing documents, and understanding the idea of tolerances in here. And I just tell them, we have half a mil, right? Everything's plus or minus half a mil. And that's been our experience with the replicator. We could work pretty well with that. And if something was too tight, you could work a little bit and it fit. The sketches and I've only run these with the sketches now, not on the method, but there's definitely, that's almost too much space. We really need to cut it down. And we'll do some work, I guess, to figure out how close we should be doing it.
Yeah. Those sample parts, and you made me think about something here. I'm just going to show you a quick image.
What's funny, I don't actually 3D print that much. Because it takes so much time and it's expensive. It's really a capstone thing. Like typically it's okay. You've worked and you've generated this thing. This is now now you have it, but it's usually disappointing in the end compared to the CAD file.
Right. Yeah. Well, so what you made me think about with
Thank you, Paul.
Thanks.
Yeah,
Thanks.
thank you,
I got to cut out Adam and Dave. Thank you so much. It was very interesting.
Nice to meet you.
You got it, Paul.
Yeah. Nice
we'll
meeting you
touch.
too, Dave. Yep. We'll be in touch. See you guys. See you later.
All right. Bye-bye.
Bye-bye. Bye, Kristen.
So yeah, Dave, this it's a little blurry here, but let's see, do I have a better image of this? Probably not. So these are trays that I printed on the sketch, and they were just for kind of doing a palletizing routine with this robot arm. But what I wanted to do was can you see this little tab right here?
Yep.
So I made a little tab so the robot could come and pick up the pallet right after it finished an operation. And then I also made these little, these little notches or nubs here that so they could get stacked and fit together. And, just during my testing process, I went back into my CAD model and I just printed this. I printed the corner only. Right. So I printed 2 of the corners to see how the fitting would work. And, just looking at your student's phone stand, same thing. Just if you chop off just like a little bit where the socket is, and print that just to see how it works, it's a great control point.
Yeah, that's what we started doing. And that was nice and manageable, right? And we could turn it around and have it, a couple hours anyway.
Yep. Very cool.
So Yeah, it's
Awesome.
fun. Yeah.
Yeah.
It's,
Well, thanks for sharing, Dave. We should wrap up, but it was nice to meet you. I know that you know that we have some connection with your school, and if you want to have a more detailed conversation when you're ready to look at more equipment, or just even just ask to get some information about equipment, reach out, please.
okay, will do. Thank you guys. I appreciate it.
Thank you.
Hope to see you again.
Nice to
Kristen,
meet
thank
you.
you.
Bye.
Okay.
All right, take care, guys.
Bye.